Swayam Prabha. Digital India. Educated India.
Okay, good morning. So we're talking about this kinetic Monte Carlo simulation of a jump Markov process. So we'll continue the discussion with a few examples today. So now if you remember, when we think about this jump Markov process, we define a characteristic function, right? So W of n plus V So a jump Markov process is defined by this transition probability per unit time, that's like a rate that the system is given at time t to n, and then it basically jumps to another state n plus v, okay, n plus nu. And this is actually written in terms of two parts, one that talks about the rate and another one talks about where the end state, what's the probability of reaching this end state n plus nu. Okay, so this is basically pretty much defines any sort of jump Markov process. Now, as we discussed in the last class, what we are saying here is we try to reformulate this problem, asking about what is the time at which the next event will happen. Okay, the next jump or the next event time that has a particular distribution, right? So we talked about the next jump density. Okay, basically here we are actually thinking about event driven approach. So we are asking when the next event will happen. So the next jump density is actually written in terms of two probability functions, one that allows us to sample the next jump time, and the second distribution allows us to find out what would be the next end state is. Okay, so these things we have seen. Now, especially if you look at this particular formula, the next jump time is an exponentially distributed random variable. Okay. Now, if you recollect that we talked about various kinds of algorithm to generate random numbers, if you have a exponentially distributed, we can use what is called this inverse method to sample a variable tau from this distribution. Okay. So, sampling of tau from okay. So, by this inversion method, we would obtain tau as minus 1 by a ln of u, okay, meaning that we call a uniformly distributed random number u in the limit 0 to 1, take ln of that times minus 1 by a. This would be a sampling at time tau. Okay. So, by generating a sequence of uniformly distributed random number, we can generate sequence of exponentially distributed random number tau based on this distribution. Okay. So, now we know how to sample the next jump time, and this one will have to be defined based on the problem in hand. Okay. So, putting all this together, we can think about an algorithm, and this is in the literature, this algorithm is called a Gillespie algorithm. So, Gillespie is a person name who proposed this particular methodology of doing this event driven simulations. It's a very simple few line of codes. So, first thing is to initialization. So, you would say t naught and n naught. Okay. So, you initial the time and then the state variable at time t equal to 0 or t naught, that is initialization. Second is sample next jump time from here, from p1 of tau. Okay. So, basically what you will be doing in this particular step is you would call an uniformly distributed random variable u, and then you find tau is equal to minus 1 by a. Okay, you would sample this, then you will sample nu from this omega function, and 4 is to update. So, you will update time t equal to t plus tau, which is sampled here, and n is updated from n to n plus nu, and this will be looped. Okay. Once you update this, go back, choose a new time interval, okay, and then you find a new values, update, and this goes in a loop until how long you want to do the simulation. You can actually give a cutoff for time. You can run the simulation over a particular time t. When the time is reached, you basically stop it here. Okay. And while you update, you may also want to print some output values. For example, if you need a trajectory sample path, you may want to store or record or print t versus n as you go along, okay, so that you can use this data to post process later on. So, as you can see, this algorithm is very simple. It basically the heart of the problem is to sample the next jump time from an exponential distributed random variable, and then sampling the new state and then updating. Okay, very simple to code also, and this is very powerful because you don't have to really set up your chemical master equation, you don't have to really solve Fokker-Planck equation, you don't have to really solve Langevin equation. All you need is what is my Markov process and what are my characteristic functions. With this information, any complexity, multivariate, you can handle easily. Okay, so which is very difficult if you want to do chemical master equation or Langevin or Fokker-Planck. Multivariate problems are very difficult to handle. Whatever we have seen is mostly a single variate problems. But this one, you can have any number of variables, n1, n2, n3. You can actually define your state with many number of variables. Okay, so there's no limit to it. But at the same time, much of the cost involved are in this step, where calling a random number uniformly distributed is expensive, and then doing this particular sampling is an additional overhead, which you have to do it every time step. Every time you want to do one event, you are going to do this. Okay. There are many other algorithms to do some sort of course graining. You don't do it at every event. Maybe you do it at, so I don't want to get into those details, but this is very fundamental, very, very basic. And then in terms of saving costs, there are many other efficient programs built on this. Any question at this point? So now what I'll do is, I'll take a couple of examples where you don't have to really worry about this function. Okay. Let's say there are not many choices. Let's say you have only one choice. So you don't have to worry about this sampling at all. Okay, because there's only one particular outcome that is possible. Okay, and then later on I'll go to other example where there will be a distribution for this itself, where when an event happens, there could be multiple outcomes, and then how do we sample that? Okay, so we'll go from very simple to more complex. So the first example is the Poisson process. We know that Poisson process already has an analytical solution. Okay, so you may ask, why are we then doing this numerical method? Well, you can think about this more like benchmarking your code. Okay, you construct a Gillespie algorithm, do some simple cases for which analytical solutions are possible. So you can benchmark your code, make sure everything is under control before you go to a problem where there is no analytical solution. Okay, so here so as you know, a Poisson process is actually a one-sided random walk. Okay, it can only go forward. Okay, so here when the state, so here I am describing the state with a variable small x. Okay, at time t the state is x. In the next time interval t plus delta t, it can only go forward to x plus 1. So here we are actually discretizing the space. So x is basically incremented by 1 unit length. Okay, and that rate is actually given by this function w, going from x comma t to x plus 1. Okay, now we know in Poisson process that is a constant rate. Okay, it doesn't depend on the current position. So there is a finite possibility, there is a finite rate at which the particle is actually jumping forward at a particular rate, and that rate is a. Okay, so here you can see that it can only move forward. Also, it can only move forward by 1 unit length. It cannot go 2 unit length. It cannot go 3 unit length. So that means the new state variable new here has to be always 1. Okay, if the jump is made, it can only go forward. So there is no uncertainty about it. Okay, but the time at which this jump happens follows this particular distribution. Okay, so tau is not constant, tau is exponentially distributed. Every time you sample a tau, you can increment the position by 1 unit length. So now if you compare, so what we have here, we have this x plus 1 is equal to a, and if you match with this expression, that we are actually trying to express this characteristic function in terms of two functions, one that samples time, the other one samples the new variable. So we can actually say that this a of n comma t that I have there is actually nothing but a, and the omega of new n comma t is basically 1. This is 1 for, actually you should put this is plus 1. Okay, so this function omega is 0 for anything other than plus 1. Okay, whereas this rate of jump is given by a constant a. So if this is a case, if you write in a Gillespie algorithm, you would do initialization, and then when you come here, you would simply replace this a of n by a constant a. And here you don't really sample because nu is always 1. So here you are going to update this is equal to n plus 1 for every time step. Okay, so this is a very simple algorithm for simulating a Poisson process. Yeah. Yeah. Oh, sorry, wait. This is actually ln, yeah, this should be ln of u. Yeah, yeah, thanks, yeah. Yes, yes. So I am not putting that here because there is, that's what I am saying here. So there has to be another subroutine where you will call a, you can generate yourself or you can call with the inbuilt functions. Okay, so. So now I have another example where I am talking about a chemical reaction A going to B. So in this case, the state variable is n representing the number of molecules of A. So here the state is defined based on the number of molecules of A and B, but since we know that the numbers are conserved in this case, if I know number of molecules of A, I know what is the number of molecules of B. So essentially I can convert this into a single variable problem. Okay, so here n means the number of molecules of A. Okay, so that's the that defines the state of the system. So here the reaction is a irreversible reaction, so A can only decay. Okay, A can only decrease by 1 every time a reaction event happens. So here we are thinking about reaction as an event where this molecule A converts into B at certain random time intervals. Okay, because this molecule A to B has to overcome an energy barrier. We talked about how diffusion happens over an energy barrier, there is an associated rate and everything. So it's going to be a rare event. Okay, once in a while this molecule A is going to become B. That means number of molecules of A is going to decrease by 1. So, and that rate having time at n and t, it will only go to n minus 1. Okay, so this is a rate, and this rate is actually can be written as rate constant times number of molecules of A at that particular time. Okay, so here I am going from very constant rate to another one that depends on the current system behavior. Okay, so by matching the coefficients, we can say that A of n is nothing but Kn, and this omega is defined only for n is equal to minus 1 and 0 otherwise, because it cannot increase, and it cannot increase by 2 or it cannot decrease by 2 because it's a single step reaction. Okay, so once you have this, again you can set up this kind of a Gillespie algorithm. You would actually write here as Kn, where n is the number of molecules of A at that particular time interval. So here nu is -1, okay, uniquely defined, and then you would update n equal to n minus 1, t equal to t plus 2. Okay. The first two examples we didn't have to really sample the new state, okay, because it was either increasing by 1 or decreasing by 1 with no uncertainty. But there are other cases where there could be multiple outcomes, okay. So when you have multiple outcomes, I mean this nu can be many possible values every time a jump happens. For example, if I'm thinking about a Brownian random walk, free Brownian random walk, so I can either go forward or backward. I have two possibilities, okay. So similarly, there are many other processes where multiple options are possible, okay. So in that case, we have to choose in this step nu also based on this distribution function, okay. So now what we are saying is we are going to the definition, and then I'm actually summing over all possible nu, okay. So this W is summed over nu, A is independent of nu, and here I am summing over all possible nu. So remember, this is a distribution function for nu. When I sum over all possible nu, this becomes 1, okay. So that essentially means that this A of n comma t is nothing but sum over all possible nu of this function, okay. So that means we have to set this function for all possible nu and sum this over, that is your rate A. Now I can go back here, I can solve for omega. So omega is nothing but this divided by A, okay. In other words, this is going to be a function specific to a chosen nu, whereas this one is going to be a constant because it's sum of all the rates, okay. So I think it will become more clear when I take an example. So in the one dimensional random walk, I can write the transition probability for x plus 1 and x minus 1 because both are possible. There are two possible values of nu plus 1 and nu minus 1, and here this is an unbiased random walk. So there is a constant rate with which it can jump forward or backward. If you want to do this biased random walk, you can keep this as A and this is B such that A plus B equal to 1, okay. So that you can have a biased random walk also if you like, okay. But here this is a unbiased free Brownian motion, one dimensional. So, in this case, as you would see here, our function a of x comma t, so because x is the variable here, is basically sum over all of this. So, I get 2a. Now, this omega function for plus 1 is equal to this w divided by a. So, that would be a by 2a, which is 1/2. Okay. So, this is what you would intuitively also expect, that it has a 50% chance to go forward and 50% to backward. Okay. So, that is what we are actually establishing here. A divided by 2a, so simply 1 by 2. Okay. So, if I come to this particular condition, so here I would have 2a, because this is a total rate a plus a 2a, and then you will sample the next jump time from here, and when you come to this, when you come here, so let us look at this step 3 alone. So, here we have omega of minus 1 is 0.5 or 1 by 2, and omega of plus 1 is 1 by 2. Okay. So, now we have to sample this. The way you can do that is, in this case, you call a random number uniformly distributed. Let us call this is u2, let this be u1, and then you check if u2 this is less than 0.5, choose minus 1, else that means u2 is actually larger than 0.5, choose plus 1. So, when you have a probability like this, okay, so you have a 50% chance of choosing plus 1 and another 50% for minus 1. So, in order to make a decision, you call a random number u2, this is going to be from 0 to 1. Okay. Now, here if the called random number is below 0.5, you choose minus 1, otherwise choose plus 1. This order can be changed also if you like, does not matter. So, in this particular algorithm, what you would do is initialize, you know the constant, get the next jump time. After choosing time, you find which new is going to happen, it's plus or minus 1, plus 1 or minus 1, based on this algorithm. Okay, and then you are going to update the chosen plus 1 or again minus 1, depending upon what the choice of new is, and then you are going to update this over and over, right. Let me just do that. Right. Something like that you will do. Okay. So, what I am actually doing here, if you think carefully, what I am doing is actually I am thinking about a cumulative probability. So, I have two states, plus 1 and minus 1. Okay. So, let us say this is a probability of 0.5, and then this is another probability of 0.5. So, total is 1. Okay. So, now the probability for plus 1 is 0.5 and the probability for minus 1 is 0.5. So I have constructed a cumulative distribution. Okay. So now I am calling a random number if the random number happens to be in this range, because the uniformly distributed random number is from 0 to 1 and the cumulative distribution for this also is 1. So what we do is we throw a random number and see if it falls here somewhere, we know that this event is going to happen. Okay. If not, it's going to happen here somewhere, so you will choose a second event. If it is not 0.5, 0.5, let's say if it is 0.2 and 0.8, you will have something like this. As you call a random number uniformly distributed, you have more chance of hitting this region than this one. So more often you will choose this state as per this distribution. Okay, so that's exactly what I have done here. This is a more general case which involves multiple species, multiple reaction channels and multiple outcomes when a reaction event happens. These kind of reaction schemes you will see in the papers I have uploaded in Moodle. Many of these antimicrobial resistance models or gene expression models involve multiple components and interspecies reactions. And then as you would see that setting up a master equation for such a complicated problems for multi-species is going to be very, very hard. Okay, you can of course set it up and numerically solve, but this Gillespie algorithm or numerical kinetic Monte Carlo is far more easy to code and simulate. So we will take this particular example and discuss the algorithm. In principle, the methodology is the same. It's just that it's going to require more details in terms of choosing this, okay, and defining all the rates. So now what I'm going to do is, you can look at this. This is a two independent reaction. Both are reversible. It involves species B1, X, B2, and B3. Okay, 4 species. So now we will make, we rewrite these equations into distinct reaction channels. So I say reaction 1 is the forward reaction of the first case. And reaction 2 is the reverse one. And similarly, we can decompose this also into reaction 3 and 4. Rate constants K1, K2, K3 and K4, etc. Okay, so what I have done is I have taken these two set of reactions and then I have written them into 4 distinct irreversible reactions, and then you can see that all of them are actually now written as irreversible with certain rate constants. So the reversible rate constant K2 is this reaction, the reversible one here is K4. So in fact you can treat all the species explicitly, but for demonstration what I am going to assume is I will say that only the X species of interest to me, okay, and the number of molecules of B1, B2, B3, these are other species, I am going to keep them as a constant. Okay. So this assumption is to say that there is a very large number of B1, B2, B3 comparison to number of molecules of X. So I define the state variable as only one species, which is X. Okay. Again, this is not a necessary assumption, this is for just for the demonstration purpose here. So with that you can see that the first rate, this one. So what happens here is one molecule of X combines with B1 and you get 2X. Okay. So basically in this, when this event happens, when this reaction happens, we generate one additional X molecule. So the nu here is +1. So when the state is X comma t, if the first rate happens, if the first reaction happens, X will go up by 1. And what is the rate of that? The rate of that is going to be K1 times concentration of B1, concentration of this, in this case number of molecules of X. So number of molecules of B1, I say N1, and I am going to keep this as a constant. Similarly, when I come to the second reaction, 2 molecules of A, X, give rise to 1X and 1B1. So actually I should have this as X minus 1. Okay. So one molecule actually decays and the rate of this depends on the binary collision between X molecules. So it's basically K2 times 1/2 X into X minus 1, or simply you can write K2 by 2X square, if you like, bimolecular reaction. Reaction 3, where 2 molecules are decaying with a rate equal to K3 by 2 X into X minus 1. And the fourth one, where 2 molecules of X is created when B2 and B3, whose numbers are N2 and N3 constant, times K4. Okay. So when you have a reaction network like this, what you need to do is to write up independent events like this, or the forward and backward reactions, you separate them based on the rate constant. The next thing is to write the rates for each of this, also identifying how the changes are happening. Okay. Suppose if you want to include B1, B2, B3 also, we have to have additional arguments here. We not only say X comma t, we also say what is the number of molecules of B1, B2, B3 and how B1, B2, B3 are changing when this event happens. So you can actually accumulate other variables also if you like. Okay. But here we are assuming B2, B3, B1, B2, B3, all of them are constant. So if I have X number of molecules, okay, I have X number of molecules, I am looking at how many number of possible binary collision can happen. So that would be X times X minus 1 by 2, that would be number of pair collisions you will have, right. If I have just only 3 molecules, okay, and they are all identical, right. So you will actually overcount the number, so that is why this is to subtract that out. So okay, so the first step is to define the reactions and then the rates, and then we can go about calculating the total rate A of X comma t is nothing but sum over all possible state nu. So you can see nu can be +1, -1, -2, +2, all these possibilities. Okay. So here it's going to be summed over +1, -1, +2, -2 of all these W's. Okay, which is basically sum of all these things. So now we can define the the probability for this minus 1 to happen is this. Now, based on this function, you can sample the next jump time. Once you have updated the time, you can choose minus 1, plus 1, minus 2, plus 2 based on these ones. Okay, these are all going to be fractions. When you add up, you are going to get 1. Okay. So, if you want to, when you try to simulate this particular problem, initialization, okay, then you would find this total rate A, which is basically sum of all the rates, and then based on this, you will calculate the next jump time using a random variable. Okay. After the time was chosen, now you have to choose which reaction is going to happen. Depending upon which reaction is going to happen, the new state is going to be different. So now we have 4 possibilities. X can decrease by minus 2 by reaction 4, or X can decrease by minus 1 by reaction 2. It can increase by 1 by reaction 1, and it can increase by 2 by reaction 3. So we have to choose these reactions, but these reactions are not equally likely. They do not have all 25% chance. They will have different probabilities because of the rate constants and the current state values. Okay. So they are not equally likely. So you're going to get, for the current system x comma t, you will find all the probabilities there. Okay. Let's say this can be 0.2, this can be 0.5, 0.7, this can be 0.1, 0.8, and this can be 0.2. So this will keep changing as the simulation goes on. When x changes, the probability, the relative probability will keep changing. So here, this particular cumulative distribution is at some instant time t. So the way the cumulative distribution is constructed is that first, for reaction 4, which leads to decrease in x by minus 2, that is this probability. Okay. Now I go to the next reaction, which is R2, which decreases x by -1, and I am writing a cumulative probability, which is this cumulative probability between these two reactions. And then when I go to the third reaction, I write the cumulative probability of all the three. By the time I go to the third reaction, which is the final one, the total probability has to be 1. Okay, so now I have a cumulative distribution here. Now I have to choose based on this distribution. Okay, so what I do here is I call a random number uniformly distributed in the range 0 to 1, and I find where exactly it falls in. Suppose if this random number that I call falls in here, okay, then I would choose reaction R3 and I increment x by 2. In another event, okay, let's say instead of this, I call a random number and the random number happens to be somewhere here. Then I would choose reaction R4 and decrease the number of molecules of x by 2. Okay, and then if in some other instance, if the random number happens to be here, then you would choose R1. Okay, so this is how you are going to choose which reactions are going to happen. Okay, and accordingly update the state variable. Okay, so this is one simulation step. Okay, once a simulation step happens, you are going to update the time. You are also going to update x. When you update x, immediately all these fractions will change now for the next time interval. Okay, and this cumulative distribution will adjust accordingly. Okay, so what may be so it may be that in the beginning one of the reaction may be more possible to happen. As the system changes, the probability gets reweighted, then that reaction may become less and less probable. Okay, so it's going to evolve dynamically. Okay, and you can actually plot how x varies as a function of time. In this case, we kept b1, b2, b3, all of them as constant, but in fact you can also keep them variable also. Okay, more informations are given in my notes for you to go through, so we'll stop here. Class irukku.